So welcome to the afternoon session. I'm just filling in here for the chairperson. So we have a great speaker from computer science, Lynch, one of the world's experts in distributed computing. And it's very fortunate that Nancy got interested in networks of spiking neurons, and she tells us about this.
Okay, thank you, Wolfgang. Okay, so this is our work on an algorithmic theory of brain networks. And I know everybody here is from neuroscience, so please don't get too upset if I say something wrong about the neuroscience. I am a computer scientist and mathematician. Okay, so background. So I work in the field of distributed algorithms. So I have a research group that works on algorithms. So what's that? Well, typically it's concerned with communicating in wired networks, wireless networks, organizing networks, doing distributed data management, solving problems of consensus and decision-making problems, et cetera. Another aspect of what we do is falls under a topic that we could call general concurrent systems theory, which is concerned basically with modeling systems and then proving theorems about how you can construct them and why they work. Okay, so we observe that many kinds of biological systems are essentially distributed algorithms. So, for example, cells in developing organisms, they organize themselves, no central control, but they organize themselves into patterns. Insect colonies, another topic we've worked on, they cooperate to solve problems of exploring for food, allocating themselves to the many different tasks that the colony has to perform, and reaching consensus, for example, on where their nest should be located. And of interest to this audience, neurons cooperate to implement problems of focus, learning, memory. So compared to general distributed algorithms, the ones that arise in biology have certain characteristics. They use simple means of communication with chemical messages, not arbitrarily complex messages from some message alphabet. The components typically have simple state. Now, I don't know exactly how simple you might say neuron state is. It's probably more complicated than the models are describing right now. But an important characteristic is that the algorithms that occur in biology have to be very flexible, work in under different conditions, robust to when some things go wrong, and adaptive to changes. This is, for some background, this is not typically what we worry about for distributed algorithms. At least we don't emphasize it as much. There's too much emphasis maybe on just getting the most efficient algorithms. Okay, so to study biological distributed algorithms, which has now become a field. It has a workshop that's being held now for the 6th time. We ask questions like, how can distributed algorithms help in understanding the behavior of biological systems? Or how can the methods of distributed algorithms help us in modeling and analyzing biological systems? But in the other direction, maybe it helps to understand biological systems. Maybe that will help us in building better distributed network algorithms, or as we've seen at this workshop, better algorithms of other kinds like machine learning algorithms. Okay, so some of what we've worked on, I mentioned insect colony behavior, different kinds of problems. And we also have results in the past 2 years on brain networks. We studied problems called winner-take-all, which is, for us, a kind of leader election problem, singling out one neuron, similarity detection problem, and some coding problems. Okay. So more specifically to brain algorithms, our goal is to understand how computation is performed in biological neural networks in terms of distributed algorithms, using distributed algorithms methods. So the features that we're modeling in our work are spiking neurons. We use noisy firing thresholds. We take into account excitation and inhibition, restricted connectivity, synapse weights, synchronization. Okay. Of course, that's not everything. So far, we focused on fixed networks rather than on learning the networks. So we certainly are interested in learning in terms of, say, adjusting weights. But right now we're just looking at the question of what networks are the best ones to solve certain problems that might arise in the brain. So the problems we look at are actually abstractions of real problems. For example, you might want to select one neuron from a set of firing neurons. Or you might want to test similarity of input patterns. Or neural coding, data compression. So these are abstract problems that are the kinds of things that occur in the brain, but it's not trying to directly model in full detail a particular brain operation. So these are basic abstract computational primitives rather than complex real-world problems. So the questions that we ask are, well, how do the features of the model that are derived from biology affect the solvability of particular problems? So we can study whether problems are solvable or not and at what cost in terms of the models. So what's the impact of the different kinds of biological features on solvability results and on the costs of solving the problems? And what kinds of algorithms would you design with these different types of biologically inspired models? On the theoretical side, is there some interesting new theory beyond what's already been studied in computational models for biology? People have studied deterministic threshold circuit, Boltzmann machines. On the distributed computing side, distributed graph networks. So we're interested certainly in whether there's interesting new theory here. But does this theory say anything interesting about computation in real neural networks? Okay. So, for example, the kinds of issues that have come up in our algorithms are interesting uses, ways of coping with noise, interesting uses for randomness, the role of inhibition and excitation, identifying patterns that appear in solutions to many problems. So these are the kinds of things that could mean something for real neural networks. Okay. So the starting point a couple of years ago was some papers that we read by Wolfgang on the theory of spiking neural networks. Okay, so I'll start right in and describe our model. And please just ask questions, since I'm used to speaking a different kind of language from you guys. So that's okay if something doesn't make sense. Okay, so this is a stochastic spiking neural network model. So this is supposed to represent discrete time slots. So this is different from a lot of what we've heard today, where you're talking about continuous time. Since brain networks certainly have a strong notion of time, we're abstracting on the discrete side to have synchronized rounds of computation. So the notation is just saying that neuron V spikes at time t. We just say V at V super t equals 1. It's not spiking at time t plus 2. Okay, so then the picture is any particular neuron has other neurons that have incoming edges to it, and those edges have weights on them. And so you calculate at each round a potential for neuron V by adding up the potentials of all its incoming neighbors that happen to be firing. So this should be pretty common. Oh, and we're subtracting a bias or threshold that's particular to the neuron. And then what we do with this is use a sigmoid function, and instead of looking at a deterministic threshold for firing, we use the sigmoid to give us a probability of firing. Okay, so we have a noisy threshold model, a stochastic model here. Okay, so we also model inhibitory and excitatory neurons, and that just means that the weights that are outgoing from the neuron are either all positive or all negative in the inhibitory case. And we're not doing anything, at least not yet, with a lot of other biological features that ought to be interesting, like refractory periods, spike propagation delays, history, so all forms of memory. We want to model that, and we're starting to do some work on that, but nothing yet. We haven't modeled noise on synapses, but I think that could be basically absorbed into the noise that we get at the neurons, but we'll see. Okay. All right, so the neural network model is it's a weighted directed graph. The nodes are the neurons. The edges are the synapses, are connections between the neurons, and the weights are synaptic strength. So it's just a technicality. If the weight is 0, that's the same as not having an edge at all. Weight is positive, it's excitatory. Weight is negative, it's an inhibitory edge. So we're taking a complicated cell with its synapses. Well, here's just a single synapse and modeling that by an abstract edge. And an entire brain network is modeled by a directed graph. Just ask questions if something doesn't make sense. Okay. All right, so okay, in the problems we're looking at, we're saying the neurons in a network are either input neurons, the X neurons, or output neurons, the Ys, or hidden or auxiliary neurons, which I've written here as A. Okay, and just as a technicality, the input and output neurons are excitatory, but the auxiliary neurons can be anything, excitatory, inhibitory. They're just the part of the design of the network, so whatever kinds of neurons you need for designing the network, use them there. All right, so how does the network operate? It's probably already pretty obvious. At a particular moment in time, well, maybe it's not obvious because this is discrete time. So at a particular discrete time, you have a firing state for each neuron. It's either firing or not, so 0 or 1. 1 if it's firing. And then the way this operates is it goes through what we call an execution. So it's a sequence of configurations. At each configuration is obtained from the previous one by letting everybody fire according to the network dynamics. So UT is the firing state of neuron U at time t. So since this is supposed to represent a component in a system, it has inputs and outputs. The inputs are assumed to come from the outside world. We don't say what they are for this subsystem. So in terms of the modeling, the input firing patterns are arbitrary. So the network has to be able to handle all kinds of inputs. But the initial firing patterns for all the internal, the auxiliary and the output neurons are part of the network definition. We say how it's initialized. Okay, so what happens? So you have this network, and then you have to say what's the input. For any particular infinite input execution, so this is modeling what's happening throughout time, the network is going to produce not a particular output execution, but a probability distribution on executions, right? So you basically apply the stochastic firing dynamics for all the neurons at all the rounds. And this winds you up with a probability distribution on executions of the system.
So do you consider recurrent networks here or just straightforward?
Recurring. Yeah, so this is going to be an arbitrary directed graph. Well, technically, the inputs should not have any edges going to them from inside the graph because they're supposed to be produced by someone else. But everything else can provide input to anything else. Any questions? Yeah.
So you start in an assigned deterministic state or in a distribution as well?
Well, we haven't thought about distributions. We could do that, but we just either say you start in a particular state or you start in an arbitrary state. So, for instance, looking ahead a little bit, in some of our problems, we want it to converge to a certain kind of state. And we might want that no matter what state it started in. So then we could say that the network has an arbitrary starting configuration.
Excuse me.
Yeah.
You have the current state UT depends on the current state T.
This is...
There's not T plus 1?
No. So this isn't saying how the dynamics are determined. This is just giving notation for the firing state of T being just what's in the configuration T configuration T is a mapping from neurons to firing states. So this is just saying UT, which is going to be either firing or not, is whatever configuration T says for you. It's a mapping. A configuration assigns a firing state to every neuron. So we say C of U is 1 if it's firing. So this is like CT of U is 1 if U is firing at time T.
The operator will actually go to
Yeah. So. Right. So what I showed on the earlier slide about the dynamics and the sigmoid function, that's how you determine. But it's stochastic. Yeah, Wolfgang.
Did I understand the dynamics correctly on the previous slide that you don't have any postsynaptic potential, so the impact of a spike is only at the next time step, right?
That's right.
And then it's
That's
gone.
the way we're modeling it. Yeah.
So this raises a question, I think, from the biological model perspective. How large would you suggest should one think is such a discrete time step?
Very tiny. We're thinking of, yeah.
A millisecond, because then I would guess the dynamics is very different from the usual network of spiking neurons, right, where postsynaptic potential lasts 20 or more milliseconds, right? So it has a lasting.
Okay, so we may need different time scales for different activity. Yeah, for us to get started, coming from where we were, we had to fix a certain model and try to get some basic results to try to show people, the kinds of things we want to do. But what we can certainly see is that you want to generalize this model in all sorts of different directions, and it probably will give you different kinds of results. My hope is that people may be interested enough to maybe suggest some variations on it, which could lead to new insights about the different models.
Yeah. So this is for every infinite input execution. Is it the output is also clamped, right? Input-output execution, you mean, or?
No, for every input execution. So that's you specify what's going to come in on all the input neurons forever, and that will cause you to generate the behavior of the whole system forever. But it's stochastic. Yeah, right. The auxiliary and output neurons. Sorry, this is. Okay, so produces a probability distribution on infinite executions. The execution includes all the neurons. We already know what happens to the inputs because that's given to us by someone else. But the system's stochastic, the dynamics are going to determine what happens to all the internal and the output neurons.
Isn't this, this looks like awfully close to Boltzmann machine, right? Without the learning part.
I'm not sure exactly. So with the stochastic.
Symmetric weights, so it's not a Boltzmann machine.
That's the only difference.
So, all right, so the way we play games in distributed computing theory is you have a model, a distributed system model, and then you describe some problems you'd like to solve. So what's a problem in this setting? Okay, well, let's say you have some collection of input neurons, and you have some collection of output neurons. And in the special case that happens to cover the problems we've done so far, it's kind of simple. You start out with fixed behavior of all the input neurons, like they're just stuck at some value forever, or think of it as for a long time. Okay, and so what you would like to do is compute some function, but since this is probabilistic, it isn't going to be an actual function. It could be a multi-valued function with different probabilities for different outputs. So the problem is going to be cast as a mapping from the input neuron firing patterns to the output neuron firing pattern, the probability distribution on output neuron firing patterns. Well, okay, so no, in this case, we're talking about a set of possible firing patterns without the probability, and the goal is to design a network that's going to converge to one of the allowed output patterns. So we could also, the more general notion of problem that we use includes the probability for which output you produce, but I just put something simpler here. A set of allowable outputs, and you have to produce one of them. It's supposed to be a small network. We're trying to measure the size of the network as one of our costs of interest. And we'd like it to converge rapidly to an output that's allowed by this function problem definition. But of course, that can't be absolute. It's going to be with some high probability. Okay, so the complexity measures I already indicated. There'll be some static measures, like the size of the network, the number of neurons, the number of auxiliary neurons, perhaps, number of inhibitors, the maximum size of the weights that you use, anything that's just a property of the network itself. But you also want dynamic measures, like how long does it take to converge? Okay, and how long do you remain in your converged state as well? Okay. So I'll spend most of the time in the rest of the talk describing our work on one problem, winner take all, and I don't think I'll have time to get into this, so I may just flash some slides quickly there. Okay, the winner take all problem. So we presented this in ITCS, that's Innovations in Theoretical Computer Science last year. Okay, so this is something that we got from reading a bunch of neuroscience papers. So the winner-take-all problem has n inputs, and they're either always firing or always not firing. Simple case. This is a binary version of the winner-take-all problem. The neuroscience literature has with different rates for the firing. We're studying that now, but simple case is just they're firing or not. And each of the inputs has a corresponding output neuron. Okay, and so what we would like is, no matter what state you begin this network in, that's all the internal and the output neurons, no matter what firing state they start in, we'd like high probability, and we measure that with probability at least 1 minus some parameter delta. The network should converge within time t sub c, and we think of that as short because we'd like it to converge fast, to where there's only one firing output. And moreover, it should be one of those that corresponds to a firing input. So you're basically electing a leader from among the candidates. Okay? And then we would like it to remain stable with only that one neuron firing. And we can't say that it's going to happen forever, but with high probability, it should stay stable for a long time. So this is, from our point of view, a neural version of a leader election problem. We study leader election problems in other settings. On the neuroscience side, you probably, how many people know it from papers in your area? It seems to be used in attention, focus, competitive learning problems. And it's been described by Wolfgang as a nonlinear primitive, meaning I guess that you can't, that it adds extra power to standard linear threshold circuits. Okay, so here's what a solution looks like. It's very simple. And we're not saying this is what happens in the brain, but you know, it could be. And maybe some of these mechanisms would be things that people could look for to see if things like that occur. I don't know. So this basically has two inhibitors playing different roles. You have one inhibitor that we call the stability inhibitor. Now it's going to try to keep things stable once they've reached a good state. So what it does is it fires with high probability whenever there's at least one output firing, one or more. And what does this do? Well, it prevents outputs that, if there's one output firing, it prevents other outputs that didn't fire at time t from firing at the next time t plus 1. Okay? Because it has enough inhibition to prevent other neurons from starting up if they're not firing already. But before you've gotten to the state where just one guy is firing, we are using a convergence inhibitor. The other inhibitor fires with high probability whenever two or more outputs are firing. So what this does is it causes any output that fires at time t to fire at time t plus 1 only with probability about a half. Okay, so you're introducing some stochastic behavior with this second convergence inhibitor. It's trying to drive the network to the point where there's fewer neurons firing. Yeah.
What happens if they're all turned off?
If they're all turned, all the outputs are turned off?
Yeah. Sometimes 1/2 will mean 0, 0, 0.
Yeah. Well, you still have a probability of 1/2 of neurons starting to fire. So I'm going to say a bit about the proof so you can see, I guess, what some of the reasoning is. Okay, so the idea is if there's a lot of outputs that are firing, about half of them are going to stop firing at each step. So with logarithmic behavior, this is going to get down to only one firing. So with some constant probability, there's a time that's at most log n, where exactly one output is firing at time t. That's the general idea. Moreover, after that convergence time, with high probability, this output will continue to fire for a long time. That's TS. And while that's happening, only inhibitor AS, the stability inhibitor, is firing, which is preventing other outputs from starting to fire, because you already have one firing. So the thresholds have to be set in a way that the inhibitors only fire at the right threshold. So that wasn't the whole solution. Here I'm filling in all the other weights on the edges that you need to make this work. So the output neurons have a bias of 3. The weights of the edges from inputs to outputs are 3. The weights of the self loops are only 2. So they help each other. They help themselves to continue firing once they are, but their bias is 3, so they need to get something else. The weights of the edges from the outputs to the both inhibitors are 1, and the weights from the inhibitors to the outputs are -1. That's inhibitory edges. Okay, so we prove an actual theorem in our style. So assuming that, wait, somehow I skipped a slide. All right. There's one more thing, which is we're putting a weighting factor in. I wrote the numbers as if they're just simple 3, 5.5, et cetera, but they actually have to be weighted by a factor gamma. Okay. What is happening? Oh, somehow a diagram didn't appear. All right, well, here's the diagram again. Okay, so you assume that gamma is large enough. And so then what we can prove is starting from any state with probability 1 minus delta, the network is going to converge within time. Convergence time is about C log n. There's also this other factor of log 1 over delta. It's going to take longer if you need a higher probability of this succeeding. So it converges within this time and remains stable for the time Ts. Okay. So we also get some other results around this. There's an expected time bound. Then we can show that you can do better than this if you use more inhibitors. You can get faster convergence. And then we explore, well, could you solve the problem faster with 2 inhibitors? And we actually do something that you might not have seen in neuroscience. We prove impossibility results or lower bounds that say that you can't solve the problem much faster with a certain number of inhibitors. So you can't solve it much faster than our solution with just 2 inhibitors. And in fact, you can't solve it at all. You could ask a theoretical question, what if you only had 1 inhibitor? And it turns out you simply can't solve this problem, and you can prove that. Okay. So, all right, so we have our 2 yeah.
So one question, what kind of solution do you get with this network? So is it, for example, clustering the input space in an equal fashion so that every winner-take-all pattern in the output corresponds to roughly the same amount of input patterns? So what kind?
So you mean, is there fairness, like in who you choose?
Yeah, I mean, what mapping is it performing?
This actually would, well, you mean who is going to be chosen? Yeah. Because of the symmetry in the solution, it's going to be equally likely to be any of them, because they behave completely symmetrically. So it happens. We didn't.
And it's roughly.
But yeah.
I mean, of course, it's not deterministic, but it's roughly the sense of one input pattern has a high likelihood of producing one winner-take-all pattern, a particular one.
No. If you have, let's say, all the input neurons are firing, you'll have like 1 over n chance of producing each one of them. There's not a high likelihood of any particular one. Okay. So, all right, how do you analyze something like this? Well, we're using some proof techniques from distributed computing theory, and I'm going to have to watch the time, aren't I? It's a quarter after, right? Okay, so we have to show with high probability that it converges. The system is going to reach a valid configuration, WTA configuration, And stability, it should say, once it reaches there, it should stay there for a long time. Now, these are reminiscent of the kinds of properties we prove all the time for distributed algorithms. So we're kind of following the style that we've used for a long time. Stability properties are common, and we prove them using invariants. They basically say if you're in a certain type of configuration, any step you do is going to keep you in that configuration. Convergence properties are proved by showing progress through a series of milestones where you get closer and closer to the region. And there's similar kinds of arguments in control theory for continuous systems. Okay. A twist now is that we want high probability statements rather than absolute statements, so things get a little more complicated. So, for example, the stability proof, I'll just give you the flavor of it. Okay, a valid WTA configuration, sure, that's one where there's exactly one output firing, and it's one that corresponds to a firing input. But you also want the inhibitors to be doing the right thing. So in the stable state, the stability inhibitor should be firing, but the convergence inhibitor should not be firing. Okay, so you have basically the state of the entire system specified. If you have all of this, then with high probability, the next configuration is going to be identical. So that says that this is stable. And if it's high enough probability that it's identical, that will tell you that this persists for a long time. And you can quantify all that. Persists with high probability. Okay. All right, so how do you prove stability? All right, the style for invariance would basically just say what's guaranteed by a single step. So suppose you're in some configuration, and it leads to a new configuration that's probabilistic. Then with high probability, well, this first thing is just a simple observation. You never get an output firing that corresponds to a non-firing input. So once you're no matter what configuration you're in, you're very unlikely to be able to have some output start firing if its input wasn't firing. A little more interesting is if you have only the stability inhibitor firing in this configuration, then all the same outputs fire that fired in the previous one. Okay, so it's not just if there's only one firing. No matter what outputs we're firing in configuration C, if just the stability inhibitor is firing, it's keeping things the same. So the same outputs are going to be firing in C prime that were in C with high probability. Okay, also, if there's exactly one firing output in C, then you can say that in the next configuration, the stability neuron is firing, but the convergence neuron is no longer firing. Okay, so you have a bunch of facts like this, and you can kind of see, you put them together, and you can show stability of good configuration, valid configuration. Convergence, to prove that, things get a little harder because you're talking about multi-step behavior, not just what's happening in one step. So, all right, so this is like proving progress properties in distributed computing by going through a series of milestones. So this is just a depiction of, well, you're starting to accomplish something, and you might be resetting to a start state, and maybe you have n neurons firing, and you go down for a while to some smaller and smaller number, and then you get to a near valid state, technically different from a valid state, and then if you're lucky, you go to the valid state. And most of these steps, except for this last one, all the other steps are happening with high probability. So there's this little technicality. In this last step, there's some race conditions going on. So you could skip from a state where 2 or more neurons are firing to one where no neurons are firing. It's not all that unlikely, right? I mean, you'd like to say, you know, nicely you have the number of neurons that are firing at each state, but of course this is all probabilistic, and you might not. So you could go from more than 2 all the way down to 0. Another thing that could go wrong is at the point where you single out as one firing output, you still have two inhibitors firing. it takes a little time, like one more round, to shut down one of them. And if they're both firing, then there's a chance that the one output that's firing is then going to stop. Okay, so there's a little race condition. But the outcome of this is that you still have constant probability, I think it's like 1/18th or something, of succeeding. And if not, well, the proof basically starts over. You have to start allowing more outputs to, the network starts allowing more outputs to fire and then has to do this several times. I don't know if that kind of thing occurs biologically, or maybe there's something that gets rid of these race conditions. Okay, so we have our convergence lemma. The probability of reaching a WTA configuration is at least a constant. And that leads to the theorem that says that you solve the problem because you have both the convergence and the stability lemmas. Okay, so that's how we can analyze this. All right, so the rest of this is you get a faster solution with more inhibitors. So you still use one stability inhibitor, but now let's say you use a lot more convergence inhibitors to try to help you get to where there's only one firing. Let's say that they have larger and larger biases. So they're trying to detect when more and more outputs are firing. And these extra inhibitors are going to speed up the convergence when you have a lot of firing outputs, because the higher bias inhibitors are going to trigger when more outputs are firing. And the effect is that they're going to decrease the probability of continuing to fire. So instead of just half, you might get down to like 1/n. If everybody's firing, you'd like the probability to, make it close to, you'd like high probability that only one will be firing at the very next round rather than having to cut it down by a half at each round. So we can play games like that, and you get a theorem. And now this is like the kth root of log n instead of log n in the bound. Okay. All right, and then we prove lower bounds. So we have to put it, lower bounds are very hard to prove, and sometimes you have to pin down a few more assumptions on the model, which we did in this case. So we have to say the inputs are only connected to their own outputs, and the outputs aren't connected to each other. And the auxiliary neurons now are all inhibitors. That isn't necessary. We can generalize that. But these are conditions that are satisfied by our algorithms. And the proofs use something that we would call locality arguments. They're used all over the place to prove impossibility in distributed algorithms. Because, the basic limitation of distributed computing is nobody knows what's happening globally. They only know what they can see. So that limitation leads to many kinds of impossibility results. Okay, so for an easy result, suppose you just have one inhibitor. There's no network then with just one inhibitor that can solve the problem with stability time that's bigger than the convergence time. Quantify all that, but I'll just give you the idea. Suppose, what would happen if you had a WTA network with just one inhibitor? Okay, well then what happens, there's only two possibilities that are around. This guy's firing or he's not. Okay, if he's not firing, then you can show that the outputs that correspond to firing inputs had better have a good probability of firing. Because if there's no inhibition going on, how would it even get started? How would you get any outputs to fire when you're starting the network up? So you need to ensure that at least output will fire in time. And so it has to be that an output with a firing input has to have a good probability of firing. The other case, though, if A is firing, well, then you'd like it to be that any output that was firing at the last round needs a good probability of stopping, because you need the capability of reducing the number of firing outputs. No, this is not a formal proof. But the thing is that you have a combination. There's only two cases. It's firing or it's not. And neither one of these is good for stability. Right? If it's firing, then even if there's only one guy firing what you like, he's going to have a good probability of stopping. And the same kind of problem in the other case. Okay. Watch it. Okay. And you can also prove that you can't improve our solution by more than log n factor. Okay. And the idea is just that fast convergence requires a lot of inhibition when there are many outputs firing, but this inhibition is too high when there's only a few outputs firing, and that's not giving you a whole lot of intuition. But basically, with only 2 neurons, there's only basically 3 levels of inhibition that you can have, and that's not enough to draw all the distinctions that you need. Okay. So discussion part for this is just notice that we had some interesting use of inhibition. The inhibitors are used for 2 purposes, stability and convergence. So, I've seen many places where inhibition is viewed as a stability mechanism in the brain, but we see that it can also be used to drive the computation toward convergence. And then the other interesting feature is randomness. It's a source of noise, but it can also be used for something. It's a computational resource, and in this case, it's used to break symmetry among the output neurons. Okay, so I don't think I have time to do anything. I'll flash through. Our other problem is on similarity testing. If you have 2 input firing patterns, you want to distinguish the case where they're equal from the case where they're significantly different. Okay. And this is doing a testing, so there's 1 neuron that's basically going to output the answer, say, are they very similar or not? So this is the kind of thing that should appear in pattern recognition tasks. So basically, we came up with an idea for an algorithm that comes straight out of the complexity theory. It's a simple sampling algorithm. If you want to know if these 2 things are close to each other, you can sample a certain number of random positions and check whether the 2 vectors match at these positions. Well, if the 2 vectors match, then your sample is going to match. But if they're significantly different, then you'll have a high enough probability by doing the sampling of noticing that they're different. So you're basically just you're doing a sampling solution to determine if things are different. And so, all right. So I'll just say how we implement this. The equality check between the sampled vectors is simple, but then how do you actually do the sampling? And here we use an indexing module, which may not be very brain-like. It's not it wasn't designed with any biological inspiration. It's just a way of extracting the neuron in the same position in the 2 vectors. So I think because of time, I'm going to just skip through. There's a picture of how you put the pieces together for the similarity testing. And skip. Okay. And lower bounds, but never mind. Okay. Another use of randomness now for random sampling, which seems to be useful in the brain for compression, abstraction, and comparison. Okay. So as a final remark, I just wanted to talk about how we can compose. We're interested in composing little subproblems. So if we're going to solve little abstract problems in the brain, how do you put them together to solve more interesting, complex problems? So this is one example from the using indexing to do the similarity testing, but there's several others, which like using WTA to solve some problem of focusing on a particular series of inputs. And you can have composition that's, this is weird. Something got corrupted on, all right. Well, there's layered composition and composition with feedback, and this slide looked fine a few minutes ago. Very strange. Okay. So composing spiking neural networks, we're following, again, some paradigms from concurrency theory to try to develop some math foundations for composing these networks. So you basically define the behavior of a network, as I did before, define the problems that the networks are solving, and then you have results like if you compose 2 networks and you compose 2 problems, well, if this network solves that problem and this network solves that one, then the composition of the networks should solve the combined problem. This is just very basic concurrency theory. Okay, so All right. So this is our goal and some of the progress we've made, and there's some interesting issues have arisen, and they may or may not say something about biology, but we hope so. I think I ran so over time, so yeah.
I have a remark then. I think one other interesting kind of interpretation of your results in terms of biology could be that one doesn't think of single spike neurons, but assemblies of neurons.
Yeah.
Jason McLean will talk about this, and Christos Papanikis, right?
Okay.
Because then I think this timing aspect now fits quite well, I think, to your model, because an assembly is active or not, and maybe if it's active, it's for 50 milliseconds or so, and then only in the next 50 milliseconds it programs which other ones will be active or not then.
Okay, I think we would need to augment the model with some history, which is something we're doing in another paper we're working on now. But yeah, then we'd be able to remember, so you could schedule when to have the delayed effect.
I think this would be quite interesting with this interpretation of assemblies.
So Cameron, one of the authors, is now writing up what was in our very short ITCS paper into, it's now like 70 pages. It's a long thesis chapter. So this is sort of showing how the modeling works and the proofs and all of that. So it could be a good model for someone else to take a look at.
Do you find that you could use the same distributed system tools to talk about continuous systems? Or do you need something drastically different when you're talking about continuous versus discrete?
So it's an interesting question. The continuous systems are what we have here is really what you call a hybrid system. It's a combination of continuous and discrete. So there's a whole area of hybrid systems. Basically, you might regard these as some kind of approximation to a continuous system. Sometimes you're able to analyze a continuous system and then prove a connection between the discrete and to prove that they're not so far apart. So various people have worked on that sort of approach. We haven't done it in this work yet.
I'm not entirely sure if you said you had delays that you were planning to incorporate or something like that.
Planning to, yeah.
Because things like winner take all, for instance, with either asynchronous uprate or delays, the paradigm that you're working with might be drastically different, because it's not the case that all the neurons are going to be seeing the same input, so one of them sees them first and fires first, or the way you get out of loops in Hopfield network is just by asynchronous firing. Things like that might change winner take all paradigm, or in similarity measures like where you start.
Yeah, it could. We were kind of thinking that the synchrony kind of reflects the fact that the brain has pretty good control of timing. We didn't want to consider completely asynchronous systems here, because that's just too pessimistic, I think, for brain modeling.
I think going down the line, I have a general question. Aren't you worried that the distribution over hiddens typically could be very highly multimodal, right? Here you had two neurons for the winner take all. I don't know how many neurons we have for the similarity.
I don't know offhand, like square root of n, or I think. Square root of n, yeah, something like that.
So are you worried about the distribution becoming?
I guess we'd have to see what happens when we try to analyze it. I mean, we're doing some pretty simple things here. These are not like trying to look at, solving some hard brain problem. It's just.
So for the similarity, you didn't have that problem. The distribution is very simple.
Mm-hmm.